So previously, we have looked at the concept of the 6 process state, which consists of the new, ready, running, block, suspended, and also exit. Within this state, we have also covered what is being needed by the operating system, which is the process control block. The process control block is a very important data structure required by the operating system in order for it to decide, in order for it to also keep track of what are the states of the current process, what it is processing, where is it currently, okay, in order for it to successfully and efficiently manage the process and its request. So for today, we are going to look further what are the other data structure that is needed by the OS for it to assist in managing those processes. As always, before we begin, I suggest you to always take a 5-minute breaks after 15 to 20 minutes viewing of our course material. So for today, we are going to look at two parts, which is the continuation of chapter 3. We are going to look at further into the process description and control, means that what are the information needed further by the operating system in order for it to manage the process. And then we will continue to the second part, which covers chapter 4 with regard to the concept of process and threads. In the previous session, we have looked at the concept of the OS control table together with the process control block. Remember, in the OS control table, we have information such as the memory information, the file information, and also the device information. So from this information, the OS actually keep track of the process progression in the process control block and then uses that information to decide whether what happens to a process. Is it actually remain in the main memory, or is it finished and it need to actually be swapped out and actually regarded as successfully finishes to what it's doing. So for this part in process control, we are going to look further. What are the information actually is inside the process, and how does the OS uses this information to actually decide what to do with a process. So just imagine you have multiple processes coming in with unique sets of requests. For example, process 1 wants to use 10 megabytes of memory, and process 2 wants to use 30 megabytes of memory, and process 3 so on with its set of requests. So in order to keep track of the process progression, the OS uses the OS control table that if you have looked previously, together with each process control block to keep track of its progression. So each instruction is actually being tracked, and upon successfully executing those instructions, the OS will decide whether the resources that it's previously holding can be released and be given to other process. So this is how the OS uses the control table and also the process control block to keep track of each specific process's progression and request. So from the OS control table, information are further divided into two categories: the process location and also the process attributes. The process location is obtained from the process control block consisting of the progression, and also from the process location is actually telling the OS currently how many processes are actually populating the main memory and how many processes are currently waiting outside in the secondary memory. So from these two information, the OS can decide which process can actually continue to be in the main memory, which process can actually be swapped out and actually be replaced by another process coming in. A program basically describes what a process needs to do. It also describes what resources does it need. So once a program is being compiled, you have a set of instructions. So this set of instructions are given to the operating system for it to know what does a process needs in order for it to complete. So each set of instruction comes with a request for a set of resources. This is how the program code is being used for the OS to actually decide how long does a process stays in the main memory, how much resources does it need. Moving further, from the set of instruction, the OS can actually know how much memory does a process needs for it to actually finishes a set of instruction. So from there, the OS can decide, okay, process 1 can go into this much of main memory, process 2 can go into another portion of the main memory, and so on. So from this set of instruction that the OS actually reads and understood, it can actually stack those set of instruction. So let's say a process have 10 instruction and another process have also 10 instruction. It will divide equally between these two processes. So for example, process 1 can actually execute 5 processes per round. Process 2 can actually execute 5 processes per round too. So this process of deciding how much instruction can be executed per process continues further until the process successfully finishes and actually swap out into the secondary memory. So let's say you have 10 processes. So those 10 processes have to be divided equally with the set of instructions that it wants to do. So this is how the OS actually use that information to decide which process comes in, which process actually go out again after a certain period of time. Of course, for it to successfully do this, the OS itself must have a good memory management model. So this depends on the OS itself. If the programmer, let's say, programs the memory management very well, then there will be no hiccups and all the processes can actually execute successfully without problem. So those program codes and instruction is being obtained by the process attributes. So remember this, the process control block actually describes what a process needs, what it's currently doing, how much resources that is need, how much data will it processes. So these are described in the process control block. All the attributes, all the progression is inside that very important data structure. So this collection of information is further described as the process image. It means that we have the codes, we have the memory stack, we also have the process attributes. So from this process image, the OS can decide successfully and efficiently what to do with a process and its request. So from the process image, this information are extracted further by the operating system. Don't be confused, it's basically still the same thing, it's just that the information is categorized further to based on the OS understanding. So it has the user data, meaning that what program does it need to execute, it has the programs, how much instruction does it need to use, and then the instruction stack that the process needs to execute for it to successfully finishes. And this information are extracted from the OS control table and the process control block. It's still the same thing, okay? Just divided further into different categories of information from the same data structure. So the decision whether to load the process image into the main memory is based on the OS memory management scheme. In some ways, some OS actually loads the entire process image into the main memory each time during the process execution, while some other only loaded a small portion of the process image while the remaining is staying in the secondary memory. So it depends how efficient is the memory management scheme of the OS. Some OS loads the entire process image, while some will actually load some portion to save space in the main memory. So from this process image, we just take a step back and look back into the process control block, the PCB, which is the most important data structure in the process image. As we have known before, all the process requests, progression, states are being stored in the process control block. So depending on the OS, sometimes this process control block is actually categorized into these three main categories, which is process identification, state information, and control information. For the process control block, each process actually is being assigned a unique identifier. So just like for each student having a student ID, it's also the same for the process. So each process will have its unique identifier to tell the OS, okay, which process is which. Of course, by using the ID, the OS can actually keep track efficiently for each process progression. Where is it currently residing? What is it currently doing? What actually resources is it currently holding? So this is being tagged by each unique identifier of the process. So same thing also happens to the I/O tables, file tables, and also the memory tables. So each of these OS control table is being referenced and directly contain the information of each unique process progression. And also, the process ID is also being used for the process communication, because sometimes processes needs to communicate with the other processes in terms of perhaps requesting a certain set of data from another process or data structure. So by having a proper ID, so each request can be tracked down and traced in case something wrong happened. The ID is also important to actually keep track of each of the threads that is currently generated or being produced by a process, because sometimes the process have their own sub-processes. So each of these sub-processes will actually do a set of instructions and need to send back whatever it is doing to the parent process. And then this ID will generate another ID that is related to the parent. So by having a proper identification, the OS can keep track of each process progression and also its child processes. Another set of important information in the PCB is the processor state information. Basically, it just tells the OS currently what is the processor doing with the process. So it consists of the contents of the processor register, which is the user visible register and the control and status register. So this is basically having all the set of instruction needs to be done by the process, and currently what is the status of the processor with those set of instruction. So as you know previously, each active instruction is being stored in the main memory. So how does it being related to the processor? So remember, each instruction of the process needs to be actually processed by the processor. So by having a proper user visible register, the processor actually knows, okay, for this set of instruction by a process, where is it currently located? How much data needs processing? So from having the information from the PCB, the processor knows, okay, this process currently in which memory location. So I will need to actually go to that process location and do the processing with the relevant register. So once a process progression is done, then it will actually send the signal back to the OS, telling, okay, I finished this portion of instruction. Now I'm going to the next set of instruction. So each progression of the instruction successfully done by the processor is being tracked in the PCB. which is in the processor state information. What is it currently doing? What is the current instruction? What is the coming instruction needs to be processed by the processor. So what happens in the background is actually each processor have their own set of status progression. So it's basically not visible to the users, it's just visible between the processor and the operating system. So each time a processor actually successfully doing a set of instruction from a set of process, it will keep track of its progression and tell the OS, okay, currently I finished doing process 1. So next one I will doing process 2 for perhaps instruction 10 until 11, for example. So this progression is being tracked by the OS because OS also needs to know whether the CPU is actually free or not to actually do the instruction for other processes. So the third portion in the PCB is the process control information. This last piece of information inside the PCB is basically being used by the OS to control and coordinate active processes. Because basically in this third portion, it's telling it actually contain the progression information of the processes. So overall, how does a process image structure actually looks like? So you have in this picture, you actually have the three portion. You have the PCB, you have the user stack, okay, and then we have all the instruction there, and also we have the shared address space. Shared address space means that, okay, let's say in your main memory, okay, we have assigned this specific space to the specific processes, and logically inside the memory space you don't have a proper order, so you need to be assigned a certain number of the memory location. So this memory location number is actually being collected inside the process image. So where do you actually need to go? Okay, where do you need to actually be referenced? Where are you actually? So the process image contains the information, the PCB, the user stack, all the instruction necessary for a process to actually successfully finishes. So this stack of instruction of the process image is actually being used by the OS to keep track of each process progression. Okay, because each user have their own user stack and each user stack have their own set of progress. So this is how OS is using the process image to actually keep track of the process progression. So the same is also true in terms of deciding on the state of each of the process. So each process states, let's say running, ready or blocked. The information is being stored in the PCB and the PCB relays that information to the process image. And from those process image, the OS will decide, okay, this process is currently doing this. Can we actually accommodate other processes that is also requesting the use of resources on our system? So in a nutshell, the PCB is the most important data structure in the entire system because it's basically contain all the important information with regard to what a process wants, what is the process progression, and what is the status of the instruction that the process is currently doing. So without the PCB, the OS simply cannot know what the process wants and how to keep track of a process progression. So the important part is not in accessing the PCB, but in protecting the PCB from error. Because if the PCB is not designed very well, it cannot communicate efficiently what the data or information that is needed to be relayed to the operating system. So without those information, OS cannot coordinate between multiple processes and the resources that is needed. Okay, so by that, we end the first part of this session. So you can take a 5-minute break and perhaps review what we have covered so far in this session. Okay, before we continue, please have a break. So in this part, we are going to look at the different modes of operating system with regard to controlling multiple processes. In the introduction chapter, we have known that the OS actually operates in two different modes of operation. We have the user mode and we also have the kernel and system mode. In user mode is basically when we execute normal user program, like your Word program for example, and also for Excel program or perhaps your web browser. So this happens in user mode. And another mode, we have the kernel mode. So kernel mode is actually when the OS is actually operating in monitoring mode or maintenance mode. So this is where the important system program is actually being executed. So basically, what is a kernel mode? So for example, you have the engine in your car. So the user mode is that you drive the car, and then you have the kernel mode with how the engine operates. So as the user, you don't actually really care how the engine actually operates for most users. Okay, you just know that when you actually press on the acceleration, the car actually moves. So the car here have the engine. The engine is the kernel. So the kernel ensures that your system or your PC operates smoothly. So it just ensures that you have the necessary resources and whatever process that you want to run actually runs until finish. So this is why the kernel mode needs to be protected from the user. Any request from the user is processed in the kernel mode, and if something wrong happens, the kernel mode will actually do the diagnostic and decides what to do with the process. And usually, the process that is running in kernel mode are usually the maintenance processes and also the system resources management program. These are the programs that is important to ensure that your system runs smoothly and without any problem. And if some problems happen, it will actually needs to decide which process needs to continue to operate and which process needs to actually stop. Because the most important objective of the kernel to ensure that the system continues to run without a problem in order to accommodate the user's request. And from that, we have two approaches with regard to the kernel mode of operation. First, we have the kernel mode outside the user process, and secondly, we have the kernel mode within the user process. So what is the difference between these two? So we go to the next section for that. So the first approach is the outside user process. So in this first approach, we have the kernel having their own set of space in the memory. So as you know, a kernel is also a program of the OS. So it has a basic function to actually manages between multiple processes. So when it means that we are outside the user process, it means that it is separated by a process. So when a process actually finishes doing something, it will need to call the kernel and actually inform, okay, I have finished doing this, so what do I need to do next? And then the kernel comes in, do the management and tells the process, okay, you have to wait because the next one coming in is another process. So this is what it means by the outside user process. Each time a process finishes or each time something happens to a process, it will call the kernel and the kernel will actually comes in and do the management. Okay, so this is the first traditional approach of the kernel. Now the second approach of the kernel mode is where the kernel mode actually operates within the user process. So what happens is, each time a new process is loaded, a portion of the kernel or the OS function is also loaded within the process execution. So this time, after a process actually happens, they don't need to actually invoke or call the kernel because the kernel function is actually loaded with the process themselves. So each time an instruction finishes, the kernel actually sends the information directly to the OS telling, okay, this process actually finishes, okay, then we need to actually do the next process further. So what happens is that when the process finishes, the kernel function actually unloads itself and then return back those information to the core operating system. So the advantage of this is that the process can be done much more faster and the information can be actually sent a lot more faster. As we know that each process is given a certain portion of CPU time and then perhaps time with the devices and time within the main memory. So how does the process actually knows when it needs to actually go out from the certain state into another state? So this is where the process interrupts and mode switching comes in. So before we go into that, we need to look at the very beginning. What happens during process creation? So the flow is like this. Okay, so once a OS decide to create a new process, it means that when a user actually click on an app icon and then user want to actually execute. Okay, so now after that input from the user, the OS decides, okay, it's time to create a new process because the user wants to actually execute certain instruction. So what happens is that it will assign a unique process ID to the process. Okay, and then of course allocate the space for the process to actually run. The space means that inside the main memory, okay, where does it go? And then third, initialize the process control block. It means that, okay, now we need to actually collect the data needed to actually store the process progression. So this is where the PCB is actually activated. And then it will set the appropriate linkages. You know, remember the OS control table? So now you have activated the PCB and then you need to activate all the necessary linkages in the OS control table because we need to actually keep track of the resources that it wants to use and also the progression of the process. And then lastly, of course, you need to process the data and also store the data later on. So remember the flow here, you have the ID. Next, you have the necessary space. Next, you activate the PCB. Next, you do the linkages in the control table. And then lastly, you actually explore and expand the data structure. So this is what happens each time a new process is created. So after a process be created, now it needs to actually be constantly monitored and switched between different modes. Remember we have the different states before? So each of the different states need to actually be switched around because of course process have a limited time with a selected resources that it wants. So these are the types of process switching that could happen. You have the interrupt, you have the thread, and you have the supervisor call. Interrupt means that, okay, let's say you have a certain portion of time slices. So let's say each process have 3 milliseconds to execute. So after that 3 milliseconds actually finishes, it needs to be interrupted and given chance to another process. And this process of interrupt continues until the process finishes. Secondly is the thread. The thread happens if, let's say, during execution, some error happens. Okay, so a thread is activated and the OS need to take control and see what the problem is and perhaps terminate or continue a program. And then thirdly is the supervisor call. So this sometimes happen, let's say, at the user's request. You know when you click Control Alternate Delete, so sometimes the process doesn't respond. So when having a supervisor call, it means that some process actually activate the kernel mode and the OS needs to actually come and see what the problem is and try to actually solve the problem. So these are the types of process switching happens during the cycle of the process lifetime. So in between this mode switching, first of all, we need to look at what happens to the processor. So first of all, if let's say the process executed as planned according to the pre-planned execution of the process. Let's say process A executed 3 instructions, process B executed 3 executions, and so on. No interruption in the middle. So the processor execute as normal and just continue according to the pre-planned execution. And let's say if an interrupt happens and pending the processor. So let's say there is an error happening, or there is a supervisor call suddenly happening. Okay, so what happens here in the second setting is that the processor need to actually save the program counter, meaning it save the progress with the current process, and then actually store that information and switch to the user mode and wait for the OS to actually continue to what it's doing in the kernel mode. And let's say once the problem actually finishes and being settled, then the processor will look back at the save program counter and continue from that progression. So this is what happens to the processor during the mode switching of execution between user mode and kernel mode. So how does the process actually save its progress during the change of the process state? So first of all, we look at the context of the processor. Okay, so remember in the process control block, we have the context information, which is the current state of the process. What is it currently doing? Which instruction is it currently operating, for example? So it will save the context of the processor. What does the processor actually doing when it was actually going to switch to another mode? And then it will update the PCB. So the context of the processor is being saved and updated into the PCB. Just like when you are playing a game, you are saving your progress. So this progress is being saved in the PCB. And then it will move the process control block of this process to the appropriate queue. Remember, we have the block queue, we have the suspend queue, we have the ready queue. So this is where it's being moved according to the progress of the process. And then it will select another process for execution. Remember, you have multiple processes waiting to be executed. So let's say currently process 1 is being switched to another state. So next one, what to do with process 2 and 3, for example. Next, update the PCB for the selected process. So now, let's say we are loading process 2. So now we activate process 2 and then try to see what we can do with the process. And then update the memory management data structure. Remember, we have the allocated spaces for the program, for the processes. So we need to update. Okay, currently we are doing process 2 next. Where is process 2 currently located in the main memory? So we need to update the progression for process 2 next. And then restore the context of process 2. Okay, so this continue until all the processes actually finishes execution. Okay, so we need to actually save the context of the processor, update the PCB, and also update the control table and also the memory management data structure. Now for this part, we are going to look at some of the security issues which related to the process management and also the protection of your operating system. So as we all know, the OS actually contains the memory management scheme in order to ensure that the process executes when it wants and with the resources that the OS actually manages. So for that, we need to actually ensure that all the processes and all the important programs in the system are actually protected. So in terms of threats to a system or operating system, we usually actually categorize this into two categories. First, we have the intruders, which is the physical person. And then secondly, we have the malicious software, which is always being used by the intruders. In terms of the intruders, there are three classes. First of all, the masquerader. The one is not authorized to use the system and try to actually penetrate the system and act as a legit user. And then secondly, we have the misuser, users that have the right privilege but is misusing the privilege. And third, we have the clandestine user, which actually impose their control on a user account and then make it as their own. And then from this, usually the main objective is to actually execute certain processes that is actually protecting the system by actually overcoming those protection mechanism. And for doing that, usually they have the help of using malicious software such as malware or viruses. The most common countermeasures to those threats are, first of all, we have the intrusion detection system. So intrusion detection system must constitute of the three logical components. We must have the sensors, we have the analyzers, we have the user interface. So the sensors means that what are the mechanism is there in the system to detect if any suspicious thing actually enters into the system. You have some sort of way to identify the difference between a legit process and a illegitimate process, for example. So we have to differentiate between normal program and also a virus program. That is the most basic function of a sensor. And then secondly, we have the analyzers. How to differentiate between a normal program execution and perhaps a program execution from a virus. So this is also one of the requirements in the IDS system. And of course, the most important part is the user interface. Because the user need to actually make use of the data being analyzed and how to actually do the next action in case detection successfully happens. So these are the three components of the IDS to make it successfully working in order to control the threat coming into the system. So the second countermeasure in order to counter those threats to the system is to have proper authentication. Authentication means that you have a proper way to actually recognize or differentiate between a legit user and perhaps an intruder coming into the system. For example, when you're actually using your online account in Moodle, for example, we have the basic username and password. So for other types of authentication, we have these three portions. Okay, we have something that the individual knows, particularly the password. We have something that user possesses, which is sometimes you have the key card, and also something that the individual does, let's say certain gestures. And now we also have something that the individual is, which is the use of biometrics. So these authentication methods can sometimes be combined to enhance the security of authentication. Next in the countermeasure against threat is of course having proper access control. Previously you have authenticated and verified the users. So what happens next? So usually each user have a set of things that it can actually do on a system. So for example, an admin can actually do user management, while a particular normal users can actually execute normal program. So by having proper access control, you decide or you manage how user actually use your resources in the system. And the last countermeasure is you have the use of firewalls. So basically, a firewall is a dedicated software or hardware that you can filter what is coming in and out of your computer or machine. So you can decide, for example, what website can a user actually access or what type of messages actually comes in into the network. So this depends on how you're actually going to set up your security. Either it's being very strict or perhaps depends on the location of the server or the machine. If let's say the server contains perhaps less important information, then you perhaps can authorize certain files or programs or even website that can be accessed by the user from inside your organization. Okay, and then perhaps if you have very private files or perhaps very secretive information that you want to protect, then you have to perhaps set up the firewall to be more stricter and perhaps more restrictive to other files that are coming in or coming out from the location that you want to protect. Okay, so for that, we end this part. Okay, take a 5-minute break and then we continue to the next section.